Next, we're going to talk about how to rationalize the denominator. So why do we rationalize the denominator? When do we need to do this process? So normally, unless your instructor tells you otherwise in the future, so in Math 150 or future math classes, you would need to ask your instructor, is it okay for us to leave radicals in the denominator or fractions in the radical? So in this class, it is not okay because we're learning how to remove them. That is what the process of rationalizing the denominator means. So we do not want radicals in the denominator. So like here, we don't want a radical to be left down in the denominator. It's improper to leave it like that. And we don't want a fraction to be left inside the radical. So if we look at some of the problems we did previously in the last video, you could see that the answer to this problem right here has no radical in the denominator. Or this problem here, there is no radical in a denominator. Or this problem here just has a 7. There's no radical in the denominator. Same thing here. So the next set of examples, we're going to have an issue. We're going to have a radical that's stuck in the denominator, and we're going to have to do this process of rationalizing the denominator. And if you do it correctly, there will be no radical left in the denominator when we're done. So to rationalize the denominator, it will remove a radical from the denominator, and what we need to do is we need to multiply the numerator and the denominator by a radical that will get rid of the radical in the denominator. So let's think of a simple example of why this works. If I have 2/3 and I go multiply 3 by, let's say, 4, then I would have 2/12, which 2/12 is 1/6. They're not equal. They're not equal because I only multiplied the denominator. I didn't multiply both by 4. So if I go multiply the 2 by 4 as well, now we're going to be happy because 2 times 4 is 8. And 8/12 simplifies back to 2/3. Now we're good. So the reason we're allowed to do what we're about to do is because mathematically, when you multiply the numerator and the denominator by the same thing, what this is right here is you're really multiplying by 1. 4 over 4 is just 1. It's kind of like when you find a common denominator, as long as you multiply the denominator and the numerator by that number, it works. So here's what we're going to do. We know the quotient rule says that we could take 3/7 and separate it. And we need to think of something that we can multiply both the denominator and numerator by such a number, a radical, that it will get rid of the radical from the denominator. So one way to think about it is if I think about all the perfect squares. So for example, 2 times 2 is 4. 3 times 3 is 9. 4 times 4 is 16. 5 times 5 is 25. 6 times 6 is 36. 7 times 7 is 49. So if we think about these radicals that have like an answer, like that equals 6, this equals 5, this equals 4, and so on. Let's think of a number that I can multiply 7 by, that then it will equal one of these numbers on the list. So I know that I could take 7 right here and make it equal 49. So if I put another 7 here, because 7 times 7 is 49 right here, that's how I know what to put here. So again, I knew to choose 49, square root of 49, because 7 can multiply with another 7 to make the square root of 49. So that's what I'm going to multiply the numerator and the denominator by, because this equals 1 right here. So now we have the square root of 3 times the square root of 7. That's the square root of 21. And then we have the square root of 7 times the square root of 7, which is the square root of 49, which is exactly what we wanted. Because now the square root of 49 is no longer in a radical because the square root of 49 is 7. Okay, and then before we say we're done, we just need to make sure, can 21 be simplified? So if I make a factor tree, you can see it doesn't have any common numbers there. So that's it. That is our final answer. Now, remember that we can't do this. We can't do, 7 goes into 7 once and it goes into 21 3 times. We can't do that because the 21's in the radical and the 7 is not in the radical here because square root of 49 was 7, not square root of 7. So that is our final answer. Okay, so in this problem here we have a radical in the denominator. We said that we don't want that. So we learned about the quotient rule that says that we can put them together. So what I'm going to do is I'm going to put them together so that way I can simplify 44/6 and I could now have 22 over 3. So what I did by joining them was now I was able to divide out a 2 and make the number simpler. But now I have an issue. Now I have a fraction in the radical. So now I'm going to split it apart. And now I still have an issue. I have a radical in the denominator. And we just said when we rationalize a problem, we cannot leave a radical in the denominator. So now I'm going to start the process of rationalizing. So to do that, I need to pick a number from this list that 3 can divide into. So 3 can divide into 9, so I'm going to pick 9. So if I multiply 3 by another 3, then I would get square root of 9. So that's how I know what to use. So now I'm going to multiply straight across. I'm going to get the square root of 66 over the square root of 9. And now, if we did this right, square root of 9 is 3. Now I'm happy. I don't have a radical in the denominator. Now before I'm done here, I have to make sure, if I make a factor tree, that it doesn't have any common numbers. So if I do my factor tree here, you could see that there are no perfect squares that go into 66. In other words, method 1, none of these numbers go into 66. So our final answer is the square root of 66 all over 3. Make sure when you are doing your connect homework that you click out of the radical when you type in, for example, the 3. You want to make sure that it doesn't get typed in to connect like this, because then that would be wrong. The 3 here is not in the radical, just the 66 is. So we can't do this. 3 goes into 66 22 times. We can't do that because the 66 is not 66. It's the square root of 66. Okay, so I'm going to do this problem again. Here we made 3 times 3 equal the square root of 9. Square root of 3 times the square root of 3 is square root of 9. I'm going to do it again. So I'm going to try to get rid of this square root of 3 from the denominator. So we picked 9 last time because 3 can go into 9. But can't 3 also go into 36 and 81? So any of these numbers would work. This one was the best one because it was smaller. So I'm going to redo this problem just to show you, for example, that you could pick any number from this list. And I need to take the square root of 22 over the square root of 3. And if I pick 36, then I would need to multiply 3. 36, 3 goes into 36 12 times. So I would need to multiply by the square root of 12. So then we'd have 3 times 12 is the square root of 36. But then look at what happens here. I'd have to do 22 times 12. So because I picked a bigger number here instead of this one here, the problem that we did over here, it only made 66. I only had to do 22 times 3. It made a smaller number to work with here. But if I pick 36, since 3 can go into 36, now I'm going to have 22 times 12 in the numerator, which is 264. So the whole point of doing this, rationalizing, is because now we can simplify the square root of 36, and now it's 6. But now I have this huge number in the radical to simplify. So I would make my factor tree. I have to think of two numbers that multiply to 264. So I can do 22 times 12. And then I could do 2 times 11. And 2 times 6. And then 2 times 3. And then we make the jail. And we're looking for groups of 2. So 1, 2. So both of them pair up, but only one escapes. And then that's it. There's no other. The 3, the 2, and the 11, they don't match. So we would have an 11, a 2, and a 3 in the inside. So 11 times 2 times 3, that's 66. So we would have 2 radical 66 all over 6. So now 2/6, we can simplify that to divide them both by 2. And we'd get 1 radical 66 over 3. Now again, remember we don't need a 1 in front of the radical, because when you multiply something by 1, it's just itself. So we get the exact same answer we got here. So it's easier if you pick the smaller number. But as you can see, 36 worked as well. Okay, so let's try this problem here. So first of all, we know we're going to use this list right here, because the index here is a 2. So we need our perfect squares. And now we need to think of something to multiply this by, so that this 2 right here, I need to think of something to multiply 2 with, so that way I can square root the result. So I look at this list right here, and I need to pick which radical 2 can go into. So 2 can go into 4 right here. So I'm going to put a 2 right here, because 2 times 2 is 4. It makes this number right here. Okay, now this index is a 2, and 2 doesn't go into 1. So this x is trapped in there. But if I multiply it by another x, then x times x is x squared. And then 2 will be able to go into 2. So that's how I know to put 2x here. So think of it this way. This is the jail right here. There was only 1. You need 2 to escape. So that's why we need another x here. Alright, so now that we know 2x, we're going to multiply straight across. So 1 times the square root of 2x is just the square root of 2x. And then the square root of 2x times the square root of 2x is going to make square root of 4x squared. Now if we did this correctly, this square root of 4x squared should no longer be a square. The radical should no longer be there. So the square root of 4 is 2, right? That's what we said over here. And then 2, this index goes into the x squared once. So we have no radical remaining there. And then we cannot simplify this radical. And we can't do this. We can't say, oh, these two divide out and make 1, because the numerator is in the radical and the 2x is not in the denominator. Be very careful when you type in your answers and connect math. You need to make sure that the radical is not like this, where it looks like both of them are inside the radical. So be very careful when you type in your answers and connect math that you make sure that the denominator is not part of the radical. So be careful.